Hello and welcome to this session, Learning Outcome LO5. Understand simple nuclear and atomic physics. Today, we will learn how forces between particles work in the universe. Exchange particles are the key, mediating fundamental interactions. Explore the principles of nuclear and atomic physics through this journey. Exchange particles mediate forces between particles. Photons handle electromagnetic force, gluons manage strong nuclear force. W and Z bosons are responsible for weak nuclear force. These particles carry energy, momentum, and sometimes charge. The weak interaction is crucial for processes like beta decay. Nuclei become unstable when they have a large mass number. Neutron-rich and proton-rich nuclei face instability due to imbalances. Excited nuclei hold excess energy after reactions. Unstable nuclei decay spontaneously to stabilize. This decay is a natural quest for equilibrium. Alpha decay occurs in large nuclei, reducing mass and charge. Beta-minus decay changes a neutron into a proton. Beta-plus decay requires energy to convert a proton into a neutron. Gamma emission releases energy without changing atomic numbers. Each decay type has unique characteristics. Feynman diagrams visually represent particle interactions. Gamma rays ionize indirectly via the photoelectric effect and other mechanisms. They transfer energy to electrons, causing ionization. Gamma photons can produce electron-positron pairs. These interactions must obey conservation laws. Pair production occurs when gamma photons create electron-positron pairs. In annihilation, these particles collide, converting back into photons. Energy conservation is key in these processes. Momentum, charge, and other quantities must also be conserved. Violating these laws makes reactions forbidden. Radiation types include alpha, beta, and gamma. Sources range from natural radiation to medical isotopes. Applications include medical imaging and cancer treatment. Industrial uses like thickness control are common. Radiotherapy uses gamma rays to target cancer cells. Radioactive decay follows an exponential curve. Decay is random and spontaneous, unaffected by external factors. Spin-spin interaction influences decay spectra. Activity and half-life are key metrics. Absorber thickness affects gamma absorption. Photons can excite electrons to higher energy levels. If energy exceeds ionization energy, electrons are removed. Electron collisions transfer energy during impact. Higher energy electrons increase ionization probability. Excitation and ionization are critical atomic processes. Radioactive decay is inherently random. It cannot be predicted for individual nuclei. Decay remains unaffected by temperature, pressure, or chemical state. This unpredictability is a fundamental aspect of nuclear physics. Understanding this randomness is crucial for accurate predictions. Decay equations conserve mass and charge. Using the periodic table, these equations ensure correct nuclear bookkeeping. For example, uranium decays into thorium and an alpha particle. Such equations demonstrate the principles of nuclear transformations. Mastery of these equations is essential. Exchange particles explain force interactions in physics. They mediate forces by transferring energy and momentum. Virtual particles exist briefly during interactions. Each force has specific exchange particles like photons or gluons. Understanding these particles is vital for physics comprehension. Interactions must follow conservation rules. These rules determine if reactions are allowed or forbidden. Charge, energy, and momentum must be conserved. Baryon and lepton numbers are also critical. Violating any rule results in a forbidden reaction. Electric charge must be equal before and after interactions. Energy conservation includes rest mass and kinetic energy. Pair production requires enough photon energy for particle creation. Charge and energy conservation are fundamental. These principles guide particle reaction analysis. Momentum conservation explains phenomena like recoiling nuclei. Baryon number remains constant in interactions. Protons and neutrons have positive baryon numbers. Antibaryons have negative baryon numbers. These rules are pivotal in understanding particle behavior. Lepton number must be conserved in reactions. Electrons and neutrinos have positive lepton numbers. Positrons and antineutrinos have negative lepton numbers. Violations result in forbidden reactions. Correct application of these rules is essential. To test reactions, include all relevant particles, verify conservation of charge, energy, and momentum, check baryon and lepton numbers. Allowed reactions meet all conservation criteria. Forbidden reactions violate one or more rules. Decay curves illustrate changes in nuclei over time. They enable calculations of decay rates and half-lives. Half-value thickness is determined from absorption curves. Graphs provide insights into radioactive behavior. Understanding these curves is crucial for accurate analysis. Photon interactions transfer energy in discrete packets. Electrons transfer energy through collisions. Photon ionization depends on frequency. Electron ionization depends on kinetic energy. These processes are fundamental to atomic physics. Excitation occurs when electrons absorb energy. Ionization happens when electrons gain enough energy to escape. Both photons and electrons can cause these processes. Energy transfer determines the outcome. These interactions are key to understanding atomic behavior. In conclusion, understanding decay and interactions is essential for grasping the principles of atomic physics. Have questions? Send us a message on WhatsApp at 0748436168. See you at the next session. Thanks for your attention.